Thank you, everyone, for coming. My name is Preston Holmes. I'm part of our IoT solutions team. And today I'm going to be talking to you sort of about a cornucopia of a variety of sort of performance-related thoughts that can go into your IoT solutions. So from the very beginning, speed has been part of Google's philosophy. And this was sort of published in 10 Things We Know to be true many years ago. And in fact, back in 2009, we even began running a number of experiments of about how does speed affect the way people use Google. So we would actually inject intentional slowness into Google search to just a very random percentage of users and measure how much were they still interacting with Google, how many searches were they doing. And we noticed just introducing 1 to 400 milliseconds of delay in Google search decreased up to 0.5% how many searches people did. And this idea of very small amounts of performance impacting the way people interact with technology also applies to e-commerce. So a large e-commerce place did some research and found that for every 100 milliseconds of latency added to their experience, it actually reduced sales by 1%. So speed definitely matters. But what is speed? When we say fast, it can be an extremely relative concept, right? So when we say something needs to be fast, what do we mean? Speed, as measured through time, ranges from nanoseconds to things like weeks, months, and years. So we have to think about the context of time and speed when we talk about performance. So if we look at the very lowest scale, less than a nanosecond, what are things that happen less than a nanosecond? Well, it's the delay, the time between each clock cycle of like a 3 gigahertz CPU. Or when you think about the RF frequency and the vibration of crystals emitting signals for things like Wi-Fi, less than a nanosecond per frequency vibration. Compared to something like a microcontroller, which you might find in an IoT device, much slower. So we have 125 nanoseconds between each sort of rhythmic clock cycle on something like a 8 megahertz microcontroller. So we go up now, talking about something around 20 milliseconds. When you talk about controlling things like servos or dimming lights, you have what's called pulse width modulation. This is when you change the duration of a signal out on one of your I/O pins. And these typically are about 20 milliseconds in duration, these pulses. Going to 50 milliseconds, this is about the latency you're going to find on the network to reach kind of your nearest Google Cloud region overall. Right? It can be a little less, it can be a little more, but if you're talking about sort of within your region, it could be around 50 milliseconds at just the link side of that timing. It's also about the time it takes for somebody tapping your big toe to get to your brain. So nerves, we think of nerves and sensation as being very fast, but our nerves are actually not that as sort of fast as we think they are. This is also about the time you start to perceive, if you're watching a video, when somebody's lip sync, if the audio drifts from the picture, is about 50 milliseconds. Now, if we go to a farther cloud region, if we're going sort of, say, halfway around the world or something like that on a good connection, it can be 250 milliseconds. So you can see that this time scale is sort of in our long-distance networking time frame. It's also about the time it takes to blink an eye. So we often talk about, like, in a blink of an eye as being something very fast, but this is now something we consider rather slow from a networking point of view. So we get into the kind of next order of magnitude here. BigQuery, while it's very, very good at very fast queries across very large data sets, it does take 1 to 3 seconds to sort of plan a query in BigQuery. For those of you that live near the ocean, there's something called slack tide, which is sort of this delay as the tide sloshes in and then out. That's called slack tide. That lasts about an hour. And finally, out to a month is something that you might see. It takes about a month for a strawberry to go from flower to fruit. So if you're a strawberry farmer and you're trying to optimize operations, you probably aren't caring about 10 nanoseconds of time in the way the strawberry grows. So every scale of time has a different impact on performance. Performance is also greatly impacted by many layers in your stack. So everything from the physics of the equipment you're using up to the application layer. So down at the physics layer, this might be something like the thermal capacitance of a temperature sensor. If you're looking for 100 millisecond latency on variation of temperature, the truth is the temperature sensor itself has thermal capacitance, and you can't heat it up or cool it down that fast. It has its own inertia. So the physics can't give you that kind of time resolution of temperature. On the device, you're going to deal not only with things like the processor speed, but also if you're using any sort of analog to digital converter, we'll talk about the performance of those systems. You've got to send this information over a potential variety of local and long-ranging communications protocols. Each of those can affect the performance. Everything you do with the data and ingesting it and processing it on the cloud side is obviously going to have some impact. And finally, there's a set of things around the way you can develop your applications and the way performance is perceived. And that gets into more about how we, as humans, can sort of be fooled into performance. And we'll talk a little bit about each of these. But before we go into them, we need to know a little bit more about how we measure and communicate when we talk about performance. And we're going to use this analogy of moving water from one place to another. And there are really three terms and three concepts that are used when measuring performance, and that is operations, latency, and throughput. So operations is essentially how many times can I do this task, say in an hour. The latency is how long does it take me to carry one bucket from point A to point B. And throughput often ends up being sort of a bit of a combination of the two, which is at the end of the hour, how many gallons of water have I moved? Now, there's more than one way to achieve throughput. So you can take three smaller buckets and move them in series, one after another, very quickly with very low latency, or you can move one larger bucket more slowly, and it results in the same throughput. You can move three buckets concurrently. And again, same latency in this situation and same throughput. Or you can combine combinations of concurrency, latency, et cetera, to increase your throughput, not necessarily by increasing the size of each payload. Now, what's interesting about these three measures is how widely they apply to a variety of different performance scenarios. So this same measurement is applied to how you measure disk operations. So operations, if you hear of IOPS, when you're talking about hard drives or spinning disk versus SSD, how many IOPS can a disk do? That's operations. So this idea of performance applies to very small local measurements, such as between the CPU and subsystems on the same board. But we can also think of them as applying to how data moves from the device all the way to the application that's running on the cloud. So first, let's start at the lower layers here. So fundamental to what, in my mind, defines IoT is analog to digital. Right? The world is full of all of this infinitely resolution analog information, and the first step in IoT is often to digitize that into something we can transmit on the wire. Now, analog signals are inherently at infinite resolution, both in time and in terms of value. So an X and Y axis, they're essentially infinite resolution. And obviously, we don't have infinite resolution in computation. So the analog to digital converter quantizes that data and samples it to turn it into binary data that we can send. And different analog to digital converters, or ADCs, have different performance capabilities. The way you measure the performance is in these two ways, resolution and sample rate. So resolution is how many different values can you apply to that y-axis. If you have, for example, a 7-bit ADC, you can only get 127 values potentially in your y-axis. And if it's 8-bit, you have 256. So that's your resolution. And then the sampling rate is how many times per second are you sampling these vertical lines, how often are you sampling the value. And while those sampling rates are often going to be very high and much higher than you're going to be sending or transmitting telemetry to the cloud, it's important to know what the performance of that sampling rate is if you're trying to observe subtle physical phenomenon that's happening at very fine resolution, either acoustic or vibrational, something subtle in your analog signal that you need to be able to capture and then convert into something you can send to the cloud. The other thing is to think about time and clocks on a device. So clocks have one set of time, which is the relative time of how many cycles it's run since it's booted. But you really need generally some form of connection to the real world time. Today, right now, it's 12:44. How does your device know that it's 12:44? And that's through the real-time clock. So these need to be set either manually through a touch panel or through some sort of protocol like network time protocol. They're usually battery backed so that if the device powers off and on again, it still has the current time. It doesn't have to be reset. The quality of these real-time clocks is measured as drift. And what's interesting, if you've ever seen air quality measurements in parts per million, drift in real-time clocks is also measured in parts per million. So 100 parts per million drift in a measurement of how good is this clock means that in 1,000,000 seconds, it will drift 100 seconds. And that's actually 8 seconds a day. You can see how that could kind of quickly build up. So actually, most real-time clocks are far more accurate than that. And this matters because time is used in a number of places in your IoT solution. First, it's used in the authentication. So you're not only checking, say, the validity of a TLS certification when it might expire, but on IoT Core, we enforce that the timing of our authentication token drift no more than 10 minutes outside of our server's time. So 10 minutes should cover most real-time clock scenarios, but if you're outside of that, we won't recognize that as a valid credential. Further, you want to have the time set across multiple devices in your servers all to as close to the same time as you can if you're trying to correlate events across multiple devices. If one device is set to one time and another device is set to another, and you're trying to understand how two events are related in time, they need to share a common time base. And finally, if you're looking at monitoring the performance of your system, and you're trying to measure latency, say, from the transmit time of a device to the cloud, you need a shared time across those to accurately measure latencies, and we're going to see that a bit later. So quick tip, we offer a very highly accurate free NTP service at time.google.com. Now, real-time is a phrase. We're going to see this a couple times. Real-time systems you may have heard of, and one of the places is as it relates to the kind of operating systems. So most of us are using a CPU and a typical Linux-like operating system where application and system processes all have access to the lower layers of the hardware through a kernel. And with a kernel, there are tasks that are running that can be preempted, and the kernel can essentially arbitrate which process gets access to the hardware. And that's sometimes not always advantageous when it comes to IoT. With a microcontroller, the application can have high priority access directly to the peripherals. And where that matters is when you're talking to hardware or sensors or peripherals that have very strict boundary timing on the, say, the durations of certain pulses that need to be consistent, your application that's communicating on that kind of protocol needs direct access to the peripherals at essentially, a potentially microsecond level accuracy. So when you hear about RTOSs or real-time operating systems, that generally means that there's not a kernel in the middle that could preempt you from getting access to the peripherals. So that's a bunch of things on your devices, but what are some places that Google invests at these lower layers of the actual physical infrastructure that can affect your performance? And I've pulled out just 3 of them. One of them is our investment in the long lengths of fiber. Now, the speed of light is about the fastest way we know to transmit information. I actually happen to sit alongside our quantum computing group, so potentially they can do quantum entanglement someday that could be somehow instantaneous, but we're not there yet, so speed of light is our best bet. Speed of light through glass fiber is a little bit slower than speed of light through air, but it's still the best we can do. So we've invested heavily in a lot of undersea fiber optic cables to make those long jumps as fast as possible. Inside the data center, we've also invested in a whole bunch of software-defined networking and a set of CLOS-based topology in our switches to make sure that we have the most throughput between services within our data center. And then finally, we have been working on custom silicon to accelerate machine learning, both training and inference. And as you may have heard just in this morning's keynote, we've launched Edge TPU to bring that kind of performance to machine learning out onto the devices itself. So these are just three areas where we're also investing in the actual physical hardware to increase performance. So now we have our sort of physical layers and hardware layers a little bit covered. Let's talk about how you package information. So when you're sending messages, you need to describe and package a message. And the first thing you want to consider is how are you going to serialize this? Are you going to use JSON or something binary? And the way you encode a message can impact how much time it takes on a device. It also impacts decoding it on the cloud side, but you might be more concerned about the duration of time it takes on the device. How large the resulting message is will affect how fast you can send it over the wire, but it's also going to affect the cost of storing these messages as they accumulate over time. And you need to consider whether these messages are important to you more from a latency point of view or more from a throughput point of view. All of these can affect the decisions around how you describe the messages. The serialization is going to decide also the format, whether or not you need to just have a schema or description of your message on either side. So some formats are self-describing and more schemaless, like JSON. Others, like protocol buffers, require that each, the sender and the receiver, know in advance the structure or the schema of the message. So Uber took quite a long look at this, and they compared across several different serialization formats and binary and compression formats. And while you can't read all of these, essentially, the y-axis is how much time did it take to encode and decode a given type. And the x-axis is what is the size of the resulting payload. And so the lower left is sort of the best, right? It took the least amount of time, and it resulted in the smallest message. And so you'll see things like protocol buffers and zlib compression and thrift down here, whereas JSON is way out here. Right? So while JSON is very comfortable and familiar to us, it's not necessarily always the most efficient way to send messages. Now moving up, this is a very rapid and high density talk. Hope you guys appreciate that. So as we go now, we're sending messages over some sort of a transport layer. There's a lot of these different protocols of communication out there. And let's quickly review on the right-hand side our sort of layers 1 through 4 of the OSI layering here, which is that the layer 1 is really, I think of it as the wires and waves, how things move as currents or radio waves through the air. Layer 2 is how you sort of frame the messages on that carrier sort of signal. And it's not until layers 3 and 4 that we really get into Internet of Things, IP protocol. However, there's a lot of information in IoT solutions that spend some part of their journey as non-IP traffic. And that might be over local area connections or wider area connections. So locally, we have a number of mesh protocols, right? So the performance of how many hops will that message make on a mesh protocol will affect your latency. Other protocols, which are more legacy or industrial, are bound by the carrier signal. So Modbus or other RS-45 type protocols, they're limited to how fast they can transmit information by their very design. On the long-range side, you have to consider whether you're most concerned with throughput, in which case you might be looking more for something like 5G, or cost and low bandwidth, which you'd be looking at something like NB-IoT or Sigfox or LoRa. So these are all essentially different levers and knobs you have on the transport layer to consider. The other one is to think about the protocol you're sending over these transports. So IoT Core, we offer both MQTT and HTTP, but there's going to be some differences. And one of the biggest ones is that MQTT is a stateful protocol, meaning you open a connection and then you can use that connection for multiple messages, while HTTP is more inherently stateless, and you need to set up and tear down a connection for each message you send. And you can see that over time, that overhead of establishing connections not only impact performance, but also power consumption. The other thing is that with MQTT, since it's stateful, when you update a device's configuration, it can be pushed essentially immediately down to a device. Whereas with MQTT, you have to poll and see if you have any update config waiting. Furthermore, HTTP is a text-based protocol. You cannot send binary payloads directly over HTTP. You have to base 64 encode them. That inflates the size of the payload. You're going to pay a penalty on the wire for those extra bytes of that base 64 encoding. Inside a message, you also need to think about, is there a way to economize and batch information in a single message? So you might say that you have many sensor readings, and they're all taken at approximately the same time. Well, you can send one timestamp and multiple readings in a single message, and you have reduced overhead of your actual payload. Now, you have to balance that benefit of combining messages into one message with the fact that if you need to process them independently, you may be paying another sort of tax for that on the cloud side, because you're going to have to unpack those messages. So the degree that you can gain efficiency in the transmitting by packing more information into a single message versus the unpacking on the cloud will be something to consider. But if you think about all of the metadata about a message that might be shared across multiple messages, that represents a set of overhead that you can economize on by using a thicker message type. All right, so very briefly, I think, how many people realize that they're using HTTP2 every day? So most people, I don't think, recognize that there's been this sort of radical transformation that's happened in HTTP land over the last several years. This is largely led by Google's efforts to really improve the efficiency in the way web content is delivered. So it used to be that you'd open a web page, the web page would load a bunch of images and pull down a bunch of CSS, and each of those was another HTTP connection. It was very inefficient. So we looked at sort of redesigning the way HTTP works. Now we open something much more like a stream that we can pipeline, multiplex multiple pieces of information over the same channel. We deal with flow control, so no head-of-line blocking, things like that. And we can push messages down. And this has really improved the efficiency of the web. We've gone one step further, and we also have an open RPC protocol that pushes our sort of API methods over HTTP2, and that's called gRPC. There's a whole bunch about gRPC I won't go into, but essentially it also allows you to define services and clients in multiple languages. And this all rides over the transport of HTTP2. So IoT Core today delivers a lot of its telemetry, essentially all of its telemetry over Cloud PubSub. And Cloud PubSub has been an early and avid supporter of gRPC as a protocol. However, PubSub isn't something that is as simple as you might think. You'd sort of imagine, oh, yeah, publish a message, and that subscriber just simply gets the message, and that's it. But there's a lot of knobs and decisions available to you about tuning the performance of PubSub. And the first is whether you do push or pull. Now, push, you have this overhead, as I was describing, with connection of one message at a time to an HTTP endpoint. It's not necessarily a very efficient way of getting a lot of throughput out of PubSub. We now support, through gRPC, streaming or async pull, in which you can establish a connection from a client and do streaming messages from PubSub. And this allows you to attain much higher throughput than you would be from even batch pulling messages. So this is something you definitely want to look at. I think a takeaway with performance in PubSub is understand that if you try a naive or simple measurement, you might need to do some tuning to get the optimum throughput out of PubSub. And one of those things is to as well parallelize consumption. So you can do streaming pull from a single thread, but then you can also have multiple threads or multiple processes doing streaming pull, and all of that will increase throughput. The other type of way in which parallelization can happen on cloud is if you're using cloud functions themselves will scale out. Each function can run concurrently across many instances. And finally, you can use parallelization in your data processing. So now we're moving up the stack now into sort of data processing, data management. So you can use techniques such as MapReduce and Apache Beam and dataflow to process data in parallel. That will get you through your data processing tasks much faster. And in fact, in dataflow, there's one particular thing I want to kind of call out, which is pretty interesting, and that is, if anyone's worked with data processing systems like MapReduce, the first task is that you divide a huge mountain of work up into smaller chunks, and then you divvy up all these chunks to all these workers. The truth is that that task of divvying up work is not a very perfect step in the process. And some workers end up with kind of a crummier batch of work than other workers, and they take longer. And so your actual job duration is really limited by the slowest worker of your set. And you can see that on the left-hand side with these long tooth combs. Those represent workers that got more work than others, and so the job does not complete until the last worker is done. With a feature called dynamic work rebalancing in dataflow, this is actually dynamically reapportioned to different workers mid-job so that the whole job completes faster. And that's not only going to be faster to sort of result, that's also less compute time you pay for because you're not paying for idle workers who have completed their task early. Now let's talk about high data rate. Whenever we're talking about like very high data rates, there's a whole bunch of things to consider. So first of all, what is your requirement around the integrity of your data? if you require very high consistency and high integrity around every message, you will need things like locks and transactions. Now, a number of database products and storage systems will give you transactions, but they all come with some performance costs. So if you need that, it's something you need to consider into sort of your performance budget. The other thing is many storage products suffer from some degree of hotspotting if you simply try to write all of your values in a very narrow key space, right? So most distributed systems use some form of distributed hash sharding to make sure that everything is spread out across many back-end nodes. And if your keys tend to all land on the same node, that system will slow down and get burdened. So if you're using things like timestamps in your keys, you need to make sure there's enough randomness in the preceding part of the key so that you're not converging on one system. And we'll see a demo of this in just a moment. The other is if you're willing to trade off some degree of durability, there's really no beating the performance of memory. I mean, nothing is faster than RAM when it comes to computation. So if you're willing to expose yourself to some risk of loss and some risk of a little bit reduced durability, you can support a much higher rate of computation if you're only keeping a value in memory. And that brings us to rate limiting. So rate limiting is something that's there to protect systems against overuse or higher costs. It's something that you should be considering in designing your systems, that you should be rate limiting any consumers of your services to protect the performance of your system. But you also need to consider how capable is that system of handling rate limiting and the back pressure you might provide. So if you're working with a legacy system, it might be more incumbent upon you to simply scale as best you can, because that system may simply break if you return a 429 like rate exceeded, right? So if it can't handle it, you might need to deal with that. You also need to be able to handle being rate limited potentially, or be aware of any rate limits of systems that you're relying on. But there are some tricks around this. So I'm going to show a demo of this kind of a quick solution. And the idea is here we're trying to write a counter value into Cloud Firestore at a very high rate. Now, Cloud Firestore has a rate limit per document of 1 write per second per document. Right? So if I'm trying to update a counter in Firestore at a very high rate, the most I can write into Firestore for that value is once per second. So what I'm doing in this solution here is I'm using Redis, an in-memory counter, and I'm updating that in-memory counter at very high rates, and then I'm using another rate limiter attached to that and writing into Firestore once every couple seconds. So let's see if I can do a quick demo of this. So here we have a Cloud Firestore and a very simple layout where we have one collection, demo, one document called counter, and one field called count. What I'm going to do is run a little kind of load tester here. And what this is going to do is hammer my cloud function. So you're going to see this cloud function's probably gone a bit quiescent. The counter will start up a little slow. But using a rate of 200 requests per second for 80 seconds, I'm going to hit this cloud function. I might refresh this. Oh, it did work. Sometimes you've got to reload this dashboard if it's lost. So you're going to see this value of the count go up. As the cloud function warms up, you'll see this increase every few seconds. But what's happening is Redis is maintaining a high-speed counter in memory, and then every couple seconds writing the current count into Firestore. So this is a rate of increase that you could never put directly into Firestore. Right? You would basically just, if you tried to write every increment of this counter into Firestore, you'd just start getting errors from Firestore because it's protecting itself with rate limiting. So this is the kind of a technique you can use to balance performance of different layers of your system with some degree of trade-off of throughput and rate and durability. All right. I'll very quickly can kind of just walk you through a little bit of what this looks like. We have a function counter limit. It establishes a rate limiter based on Redis. Actually, I have a laser pointer. I can help you guys really quickly. Here, the rate limiter is established. I check I increment Redis here no matter what, I can increment Redis, because Redis basically has close to infinite counts, the ability in this system at least. And then here I check whether my rate limiter has any available capacity. So rate limiting is usually done in some form of where you have a certain number of operations in a window of time. So I'm sort of setting a rate limit of once every 3 seconds here. And then if I have available capacity on my rate limiter, I will write out to Firestore, write out the document. That's just that's all the code for what that demo essentially does right there. So now we're up into the application layer. So a couple points, a couple slides here on the application. So the first thing you can do is when you're dealing with different types of data, and say it's time series, if you're collecting data, say, from every 30 seconds, but most of your users are interested in something that's an average of an hour, you don't need to compute that average for every user for every view, right? You should be pre-computing certain information that you know people are going to be working with in the application. There's a wide range of caching techniques out there. I'm not going to go into them all, but caching is an important part around the performance of your application. If there's certain data you know everybody is looking for, have that available in a cache somewhere, potentially even at the presentation layer. So I'm a big believer still in the power of web applications, and web applications are becoming more and more capable in the browser, in the client. You can do quite a bit in terms of pre-computing information in your local application and then sending back to cloud something every few moments. If somebody's dragging a slider, for example, you don't need to send every loop of the browser. You don't need to send a value to the cloud. You might do it only once the slider's released, that kind of thing. You can be proactive, and this can really improve the perceived performance of an application. So again, in Firestore, it has a system called Firestore Watch that allows all of the clients, all of the applications that are interested in a piece of information to watch for any change. When that value is changed in the database, it's immediately pushed out to all the clients, right? So there's no need to write a polling loop in your application if that information is pushed immediately. Firestore also has a feature called latency compensation. So in complex applications, you might have one piece of information in the application that affects many other parts of the application. And when you change a value in the client in Firestore, it actually returns the write immediately to the rest of the application optimistically, right? So this is compensating for latency to the back end. It then has metadata that tells you, is this write actually have a pending cloud write, or is it completed? And so you can differentiate that in your app. But you don't have to build your app to wait for the long trip, round trip to the response. The other thing is, again, remember when I talked about the time frame spanning from nanoseconds to minutes, performance sometimes is about minutes to hours to people, right? If you use push notifications in an application, you bring to somebody's attention that there's something happening they should care about, right? And that can get them back into the application within minutes, as opposed to at the end of the day, they think to check the status of something. So push notifications are another way of being proactive with your users. And then finally, things that I put in this category of suggested responses are, we all use every day applications that are very helpful in auto-completing, right? If you go to the same web page every day and you start to type that URL in Chrome, it ranks it up there right at the top. It knows which is most active, and that saves many, many seconds of our interactions with applications every day. So think about how to be proactive in suggesting responses at the application layer. And finally, offline. All right, so this is something where obviously as a cloud platform, we're interested in the application tying greatly to capabilities that we offer on the cloud, but we also recognize that applications still need to function offline. So if we're thinking about things in a browser, we have things that we've really been investing recently at Google called progressive web applications. It allows web applications to use local storage and web workers to maintain sort of a fully functioning experience while the machine's offline. Firestore also will sync data locally to the local storage system of the browser offline so the application can continue to function. I mentioned edge TPU earlier. The idea of running inference on the edge means that if you have a critical behavior in the use of ML on a device on the edge, that behavior needs to persist and be functional even if you've lost a connection to the cloud. So being able to do ML on the edge. And I would actually argue that be mindful about having cloud in the loop, but in the application loop in terms of the user's experience. The canonical idea that you're going to flip a light switch and the light turns on, it's probably not a best place to put a hard dependency of having cloud in that loop, right? Have that loop happen locally, offline, and then async, keep that data synchronized or report it to the cloud, but don't put a cloud path in a critical performance path in a local application experience. So monitoring, okay? You cannot improve the performance of something you're not measuring. And there's a lot you can be measuring. So you can be measuring performance of the hardware, performance of the device. You can be measuring the performance of application software either on the device or at the presentation layer. You can be measuring performance of the network, either something we provide you on our part of the network or something that you measure yourself from the end-to-end reality of your device to a server. So it's very critical. It's almost nonsensical to talk about knowing your performance or improving your performance if you don't have measurements that you can tell whether you've made an improvement. I'm going to show another brief demo. All right. Switch the order up on myself here a little bit. When you're talking about measurements of performance, it's really important to understand that some measurements are a lot more useful and valuable than others. And one of them that can be not so helpful is an average, right? This is a quick graph of two distributions of data that have the exact same average. But obviously, they're very different. If you were only measuring an average for these two data sets, they would look identical to your reporting system. You would say, oh, no, we have a average of 100. It's great. But clearly, the distribution of this data is very different. So what is common in monitoring systems is to look at percentiles or quantiles, where you're essentially looking at buckets of information across a distribution. And you're caring about potentially what are most of our requests doing, or what is our slowest 10% of all of our requests. So if you see numbers like P99 or P95, or how many nines of what your latency is at 3 nines, those kind of things, these are all dealing with quantiles and percentiles. So back to the demo. Oh no, I think my battery has died. So I have a backup. So I have a device that's been publishing, except it has tuckered out on me. So the backup here is I have a screenshot. I'm going to also see if I can't get this to come back online while I do this. But I'll go through the screenshot first. So what we have here in the screenshot is the measurement of the publish acknowledgement latency over MQTT to IoT Core. And so this is a measurement that we can't provide you on the cloud side. This can only be observed from the device side. So if a device is sending a message over MQTT, we do a couple interesting things for you on the performance side and the durability side. So what we do is when we take the message from MQTT and write it to PubSub, we will not acknowledge the message on MQTT until after it's been written to PubSub. Right? So that when you get an acknowledgement on the MQTT protocol, you actually know that that data has already arrived safely and been delivered into Cloud PubSub, and Cloud PubSub is a highly durable, highly reliable system. But you might care about, like, well, how long did that take from the device side? When do I get acknowledgement on the device side? And because the network is not a perfect system, not every message is going to have identical latency. And what you want to know when you're looking at the quantiles here is, what's the average speed of my best half of all my messages? So that would be your 0.5 here. I'm going to see if I'm lucky enough with the demo gods. Yeah, so I'm starting to get data now. I'm going to have to switch my time resolution to the last 5 minutes to get anything useful here. So you can see here that I can look at that measurement and see, as I hover over each of these, what the performance of each of these measures is, what each of these buckets is. And so you may see, or if you see a very high spread, that may or may not matter to you, right? But if you have a user who's sort of reporting, or somehow you're trying to debug something, you're saying, wow, sometimes something seems to take a long time. Is it in my system? Well, you may see something like a 95th percentile that's slower. And that might be fine, because you know that 95% of your messages are getting through within some faster rate than that. But it's good to know. And if you were simply measuring your average latencies, you wouldn't know. You'd lose that information. You'd lose that insight into what is the range or what is the distribution of performance I'm seeing in these systems. You can do the same kind of thing not only in this publish acknowledgement speed on MQTT, but at any other leg of your system. And you can, in fact, build distributed traces of these kind of things over the whole end-to-end span. So I've pulled up here also that there's the idea of monitoring not only applies to the sort of inward-looking monitoring and measuring of information around the performance of your system, but it can be externally facing through the sensors themselves. So the lower two graphs here show the light level. And if I sort of pull out the device, now that it's restarted here, it's got a little light sensor, it's got a little display, and you'll see that as it gets into the stage lighting, this should tick up significantly. And so sometimes the same kind of monitoring you're going to do might be relevant for monitoring the performance of your physical systems, right? So we've been talking a lot about monitoring the performance of the devices or the infrastructure or the cloud, but if you're interested in like the performance of, say, a garage door, right? Use a sort of trivial example here, and saying, hey, you know, the garage door is all of a sudden taking a lot longer to open, or a furnace is taking a lot longer to warm up. These are now we're talking about the performance of the actual applications of IoT as opposed to the performance of the infrastructure and the technology supporting IoT. But the truth is, it's time series data, and it's data that is operationally relevant to you. So the same tools can apply relatively equally. So demo recovery there. All right. And then just a quick comment about cost, right? Because performance can often be improved if you throw a lot of money at a problem. If you're worried about handling huge surges of information, you can simply have a lot of very expensive standby capacity ready to process it. If you want to economize on cost, you just may let auto-scaling systems sort of scale out and handle the load. One of the great things about PubSub is it has essentially instantaneous elasticity on the publishing side. It'll act as that surge tank, right? So if you all of a sudden want to publish 100,000 messages, you can do that. It might fill up a queue, and you may not want to have, 20 servers standing by expensively waiting to process them all, but you've at least handled the ingestion instantaneously. So certain things align with performance and cost, certain things are not. So IoT Core and PubSub, you're really built on bytes. You are not built to have a faster byte transmitted. So there really isn't an extra cost associated with more performance for things like IoT Core or PubSub. Other services like Bigtable, if you want more throughput and more performance, you actually do pay more for more throughput, right? So there is a correlation there between cost and performance. Memory is an expensive thing, right? If you want to have the performance of Redis for that high-speed counter, you need to essentially have RAM on hand for those kind of operations. So in general, you need to be optimizing not only for performance and cost, and you should be looking at how the impact of increasing performance increases your cost, or where you get performance essentially for free that's built into the pricing model. So in conclusion, I think, be mindful of where performance actually has impact. The phrase premature optimization is real, right? If you're worried about 20 milliseconds somewhere on a publishing speed, but you have a transmit time of 800 milliseconds over a satellite link, is that your biggest concern at the moment, right? Should you be really trying to shave 2 or 3 milliseconds or microseconds off of something on the device if it's really just a rounding error in your end-to-end latency? So consider each of these layers, right? So just to review, the physical layer, what is the, if you look at some boards, for example, I mentioned temperature, do you need to isolate the temperature sensor away from the board so that it's more responsive to changes in temperature? On the device, do you need more compute or less compute? Can you get away with an 8-bit microprocessor, or do you need something like a CPU? Do you need edge TPU on the device to do complex ML computation on the device or not? Is the communication something you want to pay for 5G, right? Do you need the throughput, or do you just care about the latency? If you don't care about the latency, can you deal with something like NB-IoT and just send up, hourly telemetry, and that's sufficient? So don't go and buy a very high throughput, high expensive connection if you are not going to sort of take advantage of it. And then on the data side, recognize that you've got everything from managed services like PubSub, which will be highly performant for you, to sort of choices you need to make. If you're going to run a VM, you'll need to do things like choose whether or not to use SSD or spinning disk, how much RAM, what instance type. All of these variables on the data processing side can impact your performance. And then on the presentation layer, on the application side, remember that when you're dealing with humans, we can be fooled, right? We can be that the perception of performance is what matters on the application side often. And so dealing with caching, even if it's not the freshest data, are your users going to be happier with a zippier experience, or do they really need the data from 1 second ago? Or can you cache for 5 minutes and everyone's just happier because the application loads instead of waiting for a bunch of back-end processes to recompute? So across the spectrum, optimize for performance. One quick plug for those who are still around tomorrow and wondering what to do. We have a project we've been working on for DevOps. So this is a project from my team to sort of make a fun game, kind of a quest and a challenge around doing DevOps live with a bunch of people and competing in time and challenges. So that's tomorrow afternoon if anyone wants to do that. I'll be around for a couple minutes. If anyone has any questions, I'm happy to entertain them. But thank you very much.